Hello, everyone. Thank you for attending this session titled, or this talk titled Funky Malware Formats. Before we actually begin, let me give you a short introduction of what this talk is going to be about. So, me and Alexandra here, both being malware researchers, are doing quite much of malware analysis. And through our daily analysis chores, we came across this interesting phenomenon where we see a lot of custom P loaders being implemented in malware. It usually happens in all kinds of packers and first stage infectors. And that kind of made us think, if we are seeing so many custom P loaders, how common would it be to actually see custom formats being used for malware? So this is the exact question that we set out to answer in this particular research. And somewhat to our surprise, we realized that looking for such custom or interesting formats is much like looking for new forms of life in outer space or looking for aliens. And luckily, we were able to compile a few examples which are pretty interesting that we found in the wild. And we would like to present them here today to you. But before we do so, I would like to introduce you to the famous alien investigators in those cases. Here they are, right here on the screen. You can see on the left-hand side, this is me. My name is Mark Lechtik. I'm the malware research team leader in Checkpoint's research group. And I'm honored to be here today with Alexandra Doniec, also known as Hashirzada, who works as a malware researcher for Malwarebytes. And without further ado, let's talk about the first category of interesting formats that we tackled, which are custom formats. And I'll let Alexandra walk you through a couple of examples of such formats.
Thank you. As Mark mentioned, these custom formats are quite rare. My idea to research them started from one adventure. Once upon a time, me and Jerome Segura from Malwarebytes were researching the Hidden B malware, distributed by Underminer Exploit Kit. Hidden B is an interesting miner that has a high-level part as well as a bootkit part. But what triggered our attention were some atypical files dropped by the exploit kit. They both had a WASM extension, and Jerome told me that it's first time he's seeing WASM files dropped by an exploit kit. They both were marked as clean by VirusTotal, but we were suspecting that they are hiding something. My task was to analyze them. I didn't know at the time that I'm about to see something unusual. I opened them in Hex Editor first, and this is what I saw. If you look deeper, you can notice that this is clearly not how a WASM format looks like. So what is this? After researching more, I came to the conclusion that what I'm seeing is something new. So it seems we found kind of a UFO that in this case stands for Unidentified File Object. Still, I didn't have the original loader, so I had to find my own way to make sense out of this. What I had were just two files in a consistent format. So I decided to follow the structure and try to understand what each field stands for. The section that stands out from the rest is a list of DLLs. Each DLL is perpended with some number. By some experiments, I guessed that those numbers means how many functions are imported from each DLL. The list of DLLs is pointed by the word at the beginning of the header. Just after that word, we have another one. It leads us to a block just after this DLL list. I loaded the full file into IDA. It helped me to notice that each D word from the block needs to be filled with some function that is later called. So it's like filling the tanks of imports in PE. It was clearly some kind of an IAD block, and those D words from the list were checksums. Fortunately, one of the two pseudo-WASM files turned out to be a loader for the other one. So I managed to find there a corresponding checksum calculation algorithm. Summing up, this is how it works. In the given example, we have 13 functions imported from the NTDLL. Their names are resolved by checksums. Once the function address is retrieved, it is filled in the IAT, replacing the checksum. I wrote a small tool that automatically resolves for me all those checksums, so I started to understand more about this format. The next field in the header was a D word. I followed it in IDA, and I noticed that it marks a start of a function. That function was not referenced by any other, so it was clearly an entry point of this module. The meaning of the next D word was very easy to guess. It was just the size of the full module. Then we have a pair of D words. The first of them denoted size of the block, and the beginning of this block was pointed by the second one. The block looked very similar to PE relocations, except that addresses were given explicitly, not like PE format where they are usually given as page plus offset. I followed this field in IDA also, and confirmed that indeed it points the addresses that needs to be relocated. This is how I figured out the full format. I wrote a loader and a parser that is available on my GitHub. Once I realized that this type of weird formats are used in Wild, I got curious to see more of them. It led me to this interesting example of Ocean Lotus. Just to recap, Ocean Lotus is also known as APT32. It's associated with Vietnam. The dropped payloads are of various types, often composed of multiple files. The file that I got it from my Twitter friend, and originally it was distributed in a phishing attack targeting activists. After being deployed, the initial executable installed itself by dropping a variety of files. Among those dropped files, two were the most interesting because they looked really unusual. One had an extension cap and another blob, but internally they seem to be designed by the same pattern. By looking at them, I guess that they are probably XOR obfuscated, so I used the repeating pattern as an XOR key. After applying the key, they started to look much more understandable, and I even noticed some valid strings inside. Although their headers had no similarity with PE format, we could find inside some artifacts typical for PEs, for example, the manifest. So I concluded that this format must have been generated by converting PE files. Also, after loading it into IDA, we could find a valid code in some of the parts. This time, fortunately, I had the complete package, so I could also run it and see what is loaded into memory. I found the same files in the XOR decoded form being loaded in executable memory. By comparing the file on the disk with the corresponding image on the memory, we could see that the beginning and the end of the file were stripped in the loading process. So probably there were some headers. Also, the additional executable page was reserved, and the imports used by the module were loaded there. After some research, I found out what was the sequence in which those files got loaded. It turned out that all the PE files dropped by this malware on the disk were just used in the loading process, but none of them really contained the core of the malware. The main malicious activities were hidden in those malicious mysterious blobs. This format seemed much more complex than the one used by the hidden B, but luckily this time I could understand it just by reversing the loader. I quickly found that both custom files are loaded with the help of the same function, so it confirmed that they are in the same format. So this is how the first header looks, the initial header that is at the beginning of the blob. It is pretty simple. First D word is skipped. Next two are used as an XOR key. So we have to apply this XOR key first to follow, to process the next part. And then we have the value that is used in a formula calculating a size that needs to be allocated for the main module. The second header that is at the end of the blob looks bigger and is more complex. Again, the first D word is skipped, and similarly, second D word contains the value that is used in another formula. This time, this formula calculates the size that needs to be allocated for this another executable area where imports are being loaded. But the part that comes next looks like a real mystery. It does not remind any part of PE format. Analyzing the loader, I realized that the authors decided to store relocations, imports, exports, and entry point all together in records of a custom format. Each record starts by the type ID. So type 1 means relocation. This record has only one argument. That means the address to be relocated. Type 2 is for entry point or exports of the file. It requires 3 arguments: the ID, address of the function to be called, and optionally the name of the function if it is an export. Type 3 is for imports, and this time arguments are 4. Type that can mean import by ordinal or by name, address of the DLL name, address of the imported function name, or the ordinal eventually, and finally the address in the module that needs to be filled in order to redirect to the import. The interesting thing is also that the addresses of the imported functions are not filled in the typical IAD. Instead, they are stored in a list of jumps. The code is emitted by the loader and returned to the aforementioned additionally reserved executable area. So as you can see, those authors did a lot to minimize the resemblance of their format to the PE format. But in most of the cases, malware authors are more lazy and only reuse existing formats, scrambling and modifying only some elements. This kind of attitude was represented by the authors of some of the Gauzy malware variants. Probably most of you have heard about Gauzy because it's quite a popular banking Trojan. It's also known under the names such as ESFB and URSIF. The source code of the original Gauzy leaked some time ago, and since then, several new variants of this malware evolved. We will be talking about Gauzy version 3 that was already described in a paper of Maciej Kotowicz. My closer encounter with this variant started from a GitHub issue. It turned out that my tool PSIF that unpacks malware by dumping the payload from the memory was not able to properly unpack Gauzy's payload. Although it managed to reconstruct the damaged PE header, but the resulting PE was still incomplete and not so easy to reconstruct the missing parts. And the missing parts were critical for the analysis because they included the entry point, imports, exports, and relocations. Well, I was curious at what stage of loading are they erased. I suspected that if, as usually, I unpack the file manually step by step, at some point I will see the loader loading the raw PE, and then I can dump it undamaged. So this is the observed loading sequence. First, we have a crypter layer, then a loader, which is proprietary for Gauzy, and this second stage loader should give us the final payload. I expected it to be a raw PE. However, the revealed payload did not look like a PE format at all. At this point, I knew that Mark analyzed also this variant of Gauzy, so I contacted him to continue this journey together.
Right, so as Alexandra mentioned, this is indeed the blob that we found, and I was reverse engineering this particular part, and what I've been able to realize actually that you can dissect or basically divide this format to 2 parts. So the first part are modified headers. Those are headers that are written by the author of this malware and are based in some way on the PE format. The second part are actual fields that are copied as is from the original PE binary. Now let's look for a second on the first header here, which seems to resemble somewhat the DOS header in the PE format. And there we can see the magic string, which in this case is PX, which led us to refer to this particular format as the PX format. And other than that, also like the DOS header, there's a reference to what is supposed to be the PE header of this format. In this case, it would point to an actual valid PE header, However, this p header will not be used. Instead, the authors of this malware decided to use a modified version of the p header, which consists of several parts. One of them has fields that were copied from the original p header, like the machine ID, sections count, entry point, and so on. And the second one are directories that are used for loading the binary. In this case, the authors used 6 directories which appeared in a shuffled order in this particular format. And let's, as an example, take a look at one such directory. Let's look at the export directory and its fields. So for this matter, the export directory consists of several fields. The first one is an RVA, or an offset, to this particular directory in the original binary. Not in this format, but in the original binary. Second field is the size of this directory. And third one is the offset to this particular directory within this modified format, which appears right after a particular section table. Then we have the fields that we already mentioned, the common fields like machine ID. In this case, it would signify the x86 platform for this particular sample. Then we have a section count, in this case 5 sections, which would have their headers in a table that appears right after this header, and of course the entry point. So really, to sum this up, we can say that this particular format was an attempt of Gauzy's authors to somewhat introduce a P format with a new flavor. And by trying to do so, they created this sort of Frankenstein that consists of both a standard P and a modified version of it. As we mentioned initially, one of the problems that Alexandra had to tackle with this particular format is that it loses a lot of critical information that is necessary for analysis during the stage of loading. Luckily, all of this information can be actually retrieved from the raw PX format, and for that, Alexandra generated a nice tool which enables you to convert such blobs from PX to the corresponding exe sample, and you can see it here on the screen. We will publish the slides later, and you could refer to this link by yourselves. The second format, or the second example of such modified formats that we stumbled upon, is the backswap malware. It's yet another banking Trojan, and it has been revealed by ESET last year. We will not talk much about the malware itself, but we will speak obviously about the underlying format. And the interesting thing here is that backswap will actually have its code run from within a blob that resides in a particular executable. Now, the interesting thing here is that this blob is suspiciously similar to a BMP format. Now, this begs the question, how would one run code from within a BMP? Well, to answer this question, let's recall for a second how BMP is built. And we can divide a BMP to 3 essential parts: file header, bitmap header, and pixel data, which would actually would have the image data within it. Now, if we focus for a second on this file header, we can break it down to several fields. The first one is a signature of this format, which is BM in this case. Then we have the size of this BMP, some padding, and an offset to the subsequent header. Now, if we look at it from a slightly different angle, we can see that BM is actually represented by the hex bytes 42 and 4D, which if we disassemble, we actually get a valid instruction. So in this case, this is increase EDX and decrease CBP. Now, following the same logic, the backswap authors actually used the size field to generate a valid instruction. In this case, they created a jump stop, a simple jump stop that would redirect execution to a particular part within the pixel data of the BMP. So the way this would work is that once the executable passes execution to this BMP format, by hitting this particular size field, execution would be redirected into a loader that resides within the pixel data. This loader would decode some code section and some custom import table. It would resolve imports within a custom import table that resides right afterwards, and that's pretty much it. But another interesting thing that we actually realized is that this is not only an executable format. So in fact, you could also plug this thing into some kind of a viewer for images, and you would see an image. Such formats where you look at them from different ways and you see different representations are called polyglots. And they are highly covered by the great Angie Albertini, which I highly recommend you to follow to see more examples. Thank you. And if we try to visualize this particular blob, then we actually get an image or something that resembles an image. So the first part of this image actually corresponds to the malware. This is the malware payload that you see right here. But actually, there's an image here. I don't know if you can guess. Can anyone guess what we see here? Well, that's Eric Cartman. So basically, this is all about this particular format. Let's move on very quickly to the last category here, which we're not going to discuss a lot. These are standard formats. Those are formats that we actually see in day-to-day life. However, some of them are so niche that the sole fact that they're used in the malware ecosystem makes them so unique. And as an example, we looked at the XCOF format, which is actually a format that is used in the AIX operating system, which is a proprietary operating system by IBM. This operating system usually is deployed on some server platforms. One example is payment switch servers, which reside within within banking like core networks, and they are responsible for processing and routing various transactions. Now, one particular case, which I think has also been discussed in this particular conference, is one where an actual XCOF malware was used to infect such server and thus create some kind of a money fraud scheme. We will actually not be able to discuss this much, but I can only say that, because of lack of time, obviously, but I would be able to say that this attack is a courtesy of the Lazarus Group. And I highly recommend you to look at an analysis by Frank Baldwin, which is also referred in our slides, which outlines very beautifully how this particular malware works. So let's reach some conclusions here. And one conclusion that we can actually say is that while those formats that we've seen, while we can break them down to several categories, in fact, they all reside on some spectrum. And that spectrum is one that we've actually seen here throughout this talk. And they range from the very standard but niche formats to formats that are modified, where the malware authors would take an existing format and would modify it to adapt it to their needs. And finally, we have custom formats, which are totally invented. They are innovative, and they introduce some creativity in this field of malware.
Those custom formats that we saw opened some new challenges in front of malware researchers. Due to their unexpected nature, they are not supported by common tools. So in order to be able to analyze them, we need to understand the format first and write a custom loader. Another thing is that those custom formats are not recognized as executable by AV scanners. So static detection is problematic or even impossible. We can scan the executable loader, but this is not the main module of the malware and probably does not even have any malicious features. Well, and the AV product still can detect the malicious activity dynamically by observing the behavior. However, the loader only is considered to be executable, so this part will be blamed for all the actions, and this will be the module sent to the telemetry system also. And the files that really contain the core malicious activities may get neglected, so we will miss some important information about the threat. So far, this type of obfuscation is not very common, and you may wonder, why is it so, and is it something difficult to prepare? But well, not really. The minimum that we have to take care of in order to be able to deploy our own custom loader and custom module are relocations and imports. So many malware authors already know how to write their own payloaders, and if you have enough competence to do this, in fact, you can as well ditch the standard and prepare something more misleading and creative.
All right, so thank you very much again for attending this talk. Obviously, we welcome any questions privately. You can approach us on Twitter or otherwise here. And we will publish these slides, and we highly recommend you to go over those links that we've added with some great resources as reference. Thank you very much for coming to this talk, and have a great evening here at SAS.